So we've been leading up to this section for a while. In Unit 3, we learned all about how to determine if a series converges or not. So far in this unit, we've talked about Taylor polynomials, and then basically about power series. What we're going to finally do now is show how to come up with the power series that represents a function f. So the first way we're going to learn to do that is if we can make our function look like the formula for the sum of a geometric sequence, then essentially we're just going to rewrite that as a geometric sequence. So ideally we're trying to find that first term on top and that common ratio on the bottom to make it look like a over 1 minus r. Okay, and again, if we can do that, then we just get to rewrite it as a geometric sequence or series the way we've done it before. And one hint I'm going to give down here is if you're unsure how to make your function look like a over 1 minus r, what I want you to do is set the denominator of your function equal to this expression, d times 1 minus b times x minus c, where your series is centered around c. Now that's a little bit complicated. It is a little bit of a handful to memorize, but I definitely think there's a lot of value in just going ahead and memorizing that expression. Okay, so let's just try a basic example first where we're not going to have to use that crazy hint. So our first problem tasks us with finding a power series representation for this function 1 over 1 minus x centered at 0. Alright, so the first thing I want to do is just see if I can make that look like a over 1 minus r. So hopefully this will just work out. So let's see, I could have a equal 1, that's the number on the top. I could have r equal x. Cool, so it's kind of in the right form. Let's make sure that's centered around the right thing. So if I write that as a power series, that would be a times r to the n, so 1 times x to the n. Then let's see, is that centered at 0 like they told us to? Yes it is, because this is x minus 0 to the n power. Okay, so without really having to do much work at all, it already looked like a over 1 minus r, so I figured out what a and r are, and now I've got my answer. Okay, so now I've written that function as a power series. The next thing I'm tasked to do is find the interval of convergence for that series. Okay, so let's use the tools we've learned to try to determine where that's going to converge. In general, when we're trying to determine the interval of convergence, or the radius of convergence, that's where we start, we should think about either a geometric series, or we could use the root test, or we could use the ratio test. Those are kind of our big three. Well, in this case, we deliberately wrote it as a geometric series. Okay, and we know that a geometric series is going to converge exactly when the absolute value of r is less than 1. So in our case, when the absolute value of x is less than 1. Okay, so for my radius of convergence, it's centered at 0, and apparently the radius is 1. So centered at 0 with a radius of 1. Okay, and normally I would say we should go back and check the endpoints. But honestly, anytime we have a geometric series, we already know it's not going to converge at the endpoints. It's not inconclusive when the absolute value of r is equal to 1. It just straight up diverges when the absolute value of r is equal to 1. Okay, so I don't even need to check the endpoints because this is a geometric series. So my answer here is that the interval of convergence for that series is, sorry, wrote it incorrectly, all the numbers from -1 to 1, not including those endpoints, which is why I'm using parentheses here.